Good, okay. Well, welcome back after the break. I hope you're all well rested and eager to look at things with a fresh mind. So let me just remind you that assignment 3, something's on the blink here. Assignment 3 has been released, so please get started on that. This is about deep reinforcement learning, and you just have to, it's only based on one, it's just based on one environment, which is this inverted pendulum, so hopefully shouldn't be too finicky for you, but so it's a very simple environment, but it's enough that you can have a go at a few of these different methods. You can look at experience replay and a couple of other things and sort of see how it speeds up the training and makes it more stable. Okay, so have a go at that. A couple of you have emailed us about issues related to assignment 2. Alex and I have been trying to work through those. So if we haven't got back to you yet, we should hopefully get back to you within the next couple of days. Okay, so, sorry, I always have too many windows. So today we're going to talk about autoencoders and then generative models. So if you cast your mind back 3 weeks ago now, we were talking about unsupervised learning. So we talked about Hopfield networks and then Boltzmann machines and restricted Boltzmann machines. So the restricted Boltzmann machines, if you remember, you had the input and then you had a hidden layer, and it was the hidden layer tried to extract certain features from the input, and then there were sort of deep Boltzmann machines and deep belief networks. So there was this attempt, this was in the period of 2006, 7 and 8, this group in Toronto, Jeff Hinton's group in Toronto, there was an attempt to sort of make these hierarchical Boltzmann machines. So you'd train one, you'd start with the input and you'd train the first hidden layer, and then you'd fix those weights, and then you'd train the next hidden layer, and so on. And they found a few tricks to train them a bit faster, but in general, once they started to get to 2 or 3 layers, the training became quite slow, and the results were okay, but not that fantastic. So then people started to sort of look around for alternatives, and so this is where they sort of started to get into the autoencoders, and finally these generative adversarial networks. Okay, so that's what we're going to talk about today. Now, these encoder networks, as I mentioned, we looked at this in some detail in the early part of the course to sort of prepare us for this. So this we looked at this in a very, very simple setting where we just had a 1 in n encoding in the input, and we were trying to reproduce the same thing in the output. And it went through this bottleneck so that the thing had to be kind of squashed or compressed to fit it into a smaller number of dimensions. So these sort of serious encoder networks are exactly the same principle, but they're on a much larger scale and often convolutional. So typically the input layer would be an image, and then you have some convolutional layers. Well, it doesn't have to be, but generally is. And then it goes through this sort of bottleneck hidden layer and then comes out again. But it's exactly the same principle. You're trying to train it so that the output reproduces the input, but it goes through this much smaller number of dimensions in the middle. So it sort of forces some compression. It forces the network to, the only way this task can really be achieved is to extract out certain features and then put those features back together to recreate the original image. And so this actually, it does exactly the same job. It does really, it's an alternative method to the Boltzmann machines, the deep Boltzmann machines. It does almost exactly the same job, and the architecture is very similar, but the training is different. This thing is trained by backpropagation, whereas the Boltzmann machine was trained layer-wise by unsupervised learning. So it's backpropagation, but this is still sort of unsupervised learning, really, because it's not, if the data is labeled, we're not making use of the labels. We're just treating the input as a set of images, and we're always just trying to recreate the original image. So yeah, technically, and again, I've tried to follow as much as possible the notation in the textbook. Let's suppose that the input is x, and then the encoder computes z equals f of x. So what's written here is x, and the hidden so the image, if it's it's helpful to always think in terms of images. The image is x, and these the hidden layer variables we call z, and these are like latent variables. And then there's a function here. So let's say z is equal to f of x. F is the function that's computed by this layer, and then if g is the function computed by that layer, then what comes out here is g of z. So when you compose these two things together, the output is g of f of x. And so the aim is to make g of f of x as close as possible to x according to some distance function. So we have some distance function L that measures the distance between x and g of f of x, and we try to reduce that distance to the smallest possible value. Now, why is this useful? Well, the one use for this, or probably the main use for this, is as pre-training. So remember, we talked about the Boltzmann machines, or the deep Boltzmann machines. You know, we fix the inputs, and we use the restricted Boltzmann machine to train the first hidden layer. Then, if we like, we may fix those weights and again use a Boltzmann machine to train a second hidden layer. And once we've done that, then sometimes would add additional layers on top, and then we train the entire thing by backpropagation to do some task, like a classification task. So this is why it's called unsupervised pre-training, because we pre-train the weights by this unsupervised method, but then that just gives us the initial set of weights, which we can then use to refine or by backpropagation, and it becomes supervised learning, because at that point, if it's a classification task, we are actually using the labels assigned to the images. And this pre-training, it was found when back in the days when people were using sigmoid activation functions, it was certainly found that this pre-training massively improved the performance. If you did this kind of pre-training and then afterwards trained the thing by backpropagation, you get a much better result than if you had just started with random weights and trained the whole thing by backpropagation. Now, in the modern era with the relativistic linear units, the ReLUs and so on, the pre-training isn't quite so important. But it's still of historical interest and of interest in certain applications. And we can do the same thing here. So the reason I mention that is because if we train this autoencoder, we can also use this as a kind of pre-training to then be refined by supervised learning. So what happens in that case, I didn't draw a picture of this, but if you can imagine it, you train this thing to reproduce the input, but then once it's trained, you chop off the top part of this network, because what we're interested really in is the bottom part of it, the encoder. So we chop off the top half, and we replace the top half of the network with a fully connected layer and then an output layer, and then we can retrain the whole thing by backpropagation. So again, it's a form of layer-wise pre-training where the pre-training is mainly for this first layer, right? And then we remove the decoder and replace it with something else. And this can be done a bit hierarchically as well. What we can do is we could train, so if it's hierarchical, again, I probably should have made pictures of this, but just try to use your imagination. So we train this thing, and then once it's trained, we remove the top bit, and then we build, so this is like a two-layer autoencoder. So after this is trained, we then create one of so let's say we chopped out this middle bit and just had a network that went from these nodes to this and then out to here. So we could train that and use it as our initial weights for these weights. But then we could stick in extra hidden layers in the middle and retrain the thing again. So then we'd have like two pre-trained layers of features, and then afterwards we could chop this piece off and replace it with a classification layer, right? So we can kind of hierarchically do this with pre-training, okay? Any questions? Yes, you're very quiet today, yes.
With the retraining,
yep.
Did you retrain all of the weights or just the new ones that you've added on top?
Oh, okay. The question is, with the retraining, would you retrain all of the weights or just the new ones you add on top? You allow all of the weights to train, but so you're just using this as like initial values normally, yeah. There are some situations. It sort of depends. There are some situations where people might fix the weights and fix the first layer of weights, but normally we do allow them to vary. Yeah. Good question. Anything else? Yep.
So in the middle layer,
yes?
the hidden, so before and after we have the same number of hidden layer. If we want to add more.
Yeah, normally, if it's an autoencoder, normally we would have the same number of layers before and after. Yeah, it doesn't have to be done that way, but by convention it usually is. So if we add an extra layer here, we normally will add an extra layer there as well. Yeah. Okay, so I think this is kind of sums up what I was just saying. So each subsequent layer is trained to reconstruct the previous. That's the other thing. Okay, so each subsequent layer could be trained to reconstruct the previous layer. So again, there's sort of different ways of doing this, but when we when we do add in these extra layers, so we can train it so that this is equal to this, but we could additionally have an extra training signal to try to make this equal to this if we want to. So we could try to make this layer reconstruct this as well as making this layer reconstruct that. Sometimes that gives a bit of a better result. And then the whole thing can be refined by backpropagation. Okay, now one of the things with these neural networks, so when I sort of showed you this original picture, I said that that there's a bottleneck, but interestingly, once we move to these larger architectures and images and so on, and if you think sort of back to the details we were looking at with these things like ImageNet, these convolutional neural networks, often the number of hidden layers, it was often the case that the hidden nodes in a layer might exceed the number of input nodes, and also the weights might exceed the number of training items. So we'll come back to this point a little later, but this idea that you've got so many free parameters, often more free parameters than data, for people who are trained in traditional machine learning, this is sort of a warning sign that you might overfit. And in the case of autoencoders, so let's think about this, like you've got the input image, and then for those typical convolutional networks, the input image, let's say, is a color image. So whatever the dimensions of it are, you've got just 3 colors, 3 channels, red, green, and blue, coming in at each pixel. But then the first convolutional layer might have 16 filters, right? So then the number of hidden units is actually, the number of hidden units in the first layer would then actually be bigger than the number of inputs, right? Because at each pixel you've got 16 channels instead of just 3. So the size of the input layer may actually be bigger. Now, of course, it's not quite clear, or we have to sort of consider the picture that involves not only the number of hidden layers but also the number of free parameters. So those 16 channels are all sharing the same weights. So the situation in that case may not be quite so bad, because even though the number of nodes is bigger, the number of free parameters might actually be less than the number of inputs. So it's sort of this slightly complicated situation. Whether it's really going to like overfit or not sort of depends on both things, the number of inputs and the number of free parameters. But there's also the question whether we have whether this is completely convolutional, or whether we have some whether we have some fully connected layer. And by the way, the pooling, we often don't use pooling. Just as an aside, when we do this kind of architecture, we often don't use max pooling. We often just have fully convolutional networks, but we reduce the size by just using a stride rather than pooling. And the reason is because the process of pooling is not easy to reverse. In some sense, we're throwing information away when we do max pooling, because we've got 4 neighboring locations, and then we're just picking the biggest value among the 4 of them. It's not easy to reverse that process. So we normally do it fully convolutional. Okay, so but when we're asked, well, I keep saying overfitting. I don't know whether it's really the word we don't know if in this context, we don't always call it overfitting. Sometimes we call it mode collapse or something like this. But the real question is that depending on the architecture, there could be a risk that the autoencoder just literally learns the identity function. Yeah, so the architecture may be such that it's possible to have weights that'll just reproduce any input exactly, and that's not what we really want to happen. What we want is, because it's only the images that we're presenting are only a subset of all possible images. In a sense, we don't want it to be able to reproduce every image identically. We only want it to be able to reproduce this particular subset closely. And if we feed it some image that's very, very different, we would prefer that it actually creates a new image that's similar to the ones with which it was presented. So we wanted to compress it in such a way that it actually identifies useful features and then builds up an image based on those features. Okay, but there's this risk that it may learn trivial identity mapping from input to output. Okay, so one way to avoid this is to just design your architecture with a sufficiently small number of weights or parameters as to make that impossible. But another way to do it is to introduce regularization. So with the regularization, we have a number of weights which it may be the case that we have a number of weights in the network which would in theory allow it to learn the identity function, but we impose a heavy penalty on the size of the weights. So this is like weight decay, either the size of the weights or the size of certain gradients of the weights. I'll talk about it in a minute, but we put some regularization term which forces the weights to have like small values or highly restricted values, and we use that to avoid this kind of learning of the identity. And there are a number of ways to do this, so I'm just going to go through each of them in turn. These are all described in the textbook in section 14.2. So there's sparse autoencoders, autoencoders with dropout, contractive autoencoders, and denoising autoencoders. So let's start with the sparse autoencoder. So in this case, we add a penalty term to the cost function based on the hidden unit activation. So if you remember when we talked about weight decay, we imposed a penalty for the size of the weights. We said that the weights should follow. Our prior assumption was that the weights themselves should follow a Gaussian distribution, and we penalized. We had a penalty term which was proportional to the size of the weight. So there was this kind of force that was trying to keep the weights themselves to small values. Now, that could be done in this case, but it's actually often gives better results to restrict not the size of the weights, but actually the size of the activations in the hidden layer. And this will be relevant. This will be relevant when we get to variational autoencoders and GANs. You see how I've got this Z here equals f of x. What we're going to be doing with this model or variations of it is that I should make this a little bit more clear. So once we train this autoencoder or something like it, then the Z, we want the Z, so if you think about the whole set of images that you're putting in, let's say that it's, let's say that there's not just one layer here, but a couple of layers, and including a fully connected layer, then these hidden nodes then would not have any spatial, the nodes in the hidden layer in that case would be not be constrained to any particular part of the image. They would just be unspatial in some sense. And we want these we're going to want these Zs to have a particular distribution, which is like a normal Gaussian distribution. If there's 10 nodes in that hidden layer, when we feed in this set of images, we would like those hidden nodes, each hidden node to follow a Gaussian distribution, and so the whole set of 10 weights follows this. We wanted to follow this 10-dimensional Gaussian distribution, ideally with a mean of 0 and a variance of 1 in every dimension, right? And if that happens, then we would be able to use this network to generate new images. You know, because if you want a new image, let's say I put in images of bedrooms as an example, and then after I've trained this thing, I want to generate a new image of a bedroom. Well, I would just choose Z randomly. I would choose each hidden value from a normal distribution with mean of 0 and variance 1, and when I feed those Zs in, an image would come out, and I want that image also to look like a bedroom. So I'm jumping a little bit ahead here with the variational encoders, but it helps us to understand the motivation behind this. And so because it's the hidden, I don't really care what the weights are, it's actually these hidden unit activations that I want to follow a Gaussian distribution. And that's why we impose this penalty term based on not based on the size of the weights, but based on the size of the hidden unit activations for a particular any particular input, right? And now, so if we had HI squared here, it would look very much like weight decay, is what we normally do in weight decay. Sometimes, instead of having HI squared, we just use the absolute value of HI. So this is called L1. So if it's HI squared, it's called L2 regularization. If it's norm of HI, it's called L1 regularization. And there's sort of, you've got to kind of try both and see which gives better results. But if we have HI squared, then it would enforce this kind of Gaussian distribution as I was discussing. If it's norm of HI, instead of imposing a Gaussian distribution, so the beauty of the Gaussian distribution is that it's radially symmetric. If I rotate it, it's preserved. But if I use this L1 regularization, then those Z coordinates, instead of being chosen like spherically, it would be more like a hypercube. So I would be, if I would want to choose those Zs I would want to choose each Zi uniformly, say between -1 and 1. So in this case, we think of each hidden node as sort of a feature that can be present or absent to a certain degree. And I mean, this is kind of maybe a little bit fanciful, but if it's a picture of a bedroom, you might have a feature stating whether there's curtains in there, whether it's a double bed or a single bed, or whatever else you might find in a bedroom. So sometimes it makes sense to have these sort of features that can't really be rotated into each other, but each one is kind of independent. Okay, so that's the sparse autoencoder. The other thing with this L1 regularization, the reason this is called a sparse autoencoder, what often happens with this L1 regularization is that certain hidden nodes become almost zero, and others are, close to a half or whatever, minus a half. And so like I said, this sort of becomes like features that are present or absent. So the hidden nodes that become zero, those features, they represent things that could exist in a bedroom but don't appear in this particular bedroom. So that's why it's called a sparse autoencoder, because a lot of the hidden nodes may be close to zero. It's by analogy with a sparse matrix. If you have a matrix where a lot of the entries are zero, we call it a sparse matrix. Okay, the second one is called a contractive autoencoder. So the penalty term here is we take the derivatives of the hidden unit activations with respect to the inputs, and we try to make them small. And in this case, we generally use L2 regularization rather than L1. I mean, this is the beauty of backpropagation and gradient descent. You can define any differentiable penalty function and feed it in there and see what happens. So because we're doing backpropagation, we have to calculate these gradients anyway, and so we can sort of throw them into a regularization term. Now, what does this really do for us? Well, one way to think about it is that it forces the model to learn hidden unit features that do not change much when the training inputs are slightly altered. Now, I'm just going to take a slight, this is a picture I didn't think to include in the slides, but I just want to take a slight detour here, because this is going to be important in a number of issues we're discussing today, is the fact that deep networks are easily fooled. This is kind of adversarial inputs. So again, this goes back to this issue. If you think about back to ImageNet and so on, these image classification networks, as I mentioned, this idea that you've got so many free parameters, in some cases you've got 60 million free parameters and only 1 million training images, it leads to a risk of overfitting. And the convolution and the ReLUs and these things and the data augmentation saves you from that to some extent, but there's still kind of a problem, and the problem manifests itself often in this kind of way. So if you know the network, well, you can actually go through this process. You need to know the network in order to really do this. If I give you the weights of the network, and if I give you the structure of the network and the weights, you can construct an image that will really fool that network, because you can start with an image of a panda, and then you can try to you could try to make you can make very slight changes to this image, which the human eye doesn't even detect, and yet the altered image, it is very confident that it's a gibbon. Well, actually, a panda and a gibbon don't look that different, but there are other examples where you can make it look like a zebra or a cloud or all kinds of things. You could actually often change one, really fool the network into thinking it's a completely different object. And I won't go through all the details of this, but it's a matter of analysing the net. You put in that particular image, and you can actually look for that image. You can try to figure out which hidden nodes are most sensitive to changes in the input, and it's kind of done that way. You figure out that certain pixels are going to make a big change. Modifications to certain pixels are going to make a big change to the value of the outputs. And so, you can fool these networks. And I think this is at least in part, this is the motivation for doing this. So you see, well, this sums it up right here. It forces the model to learn hidden features that do not change much when the training inputs are slightly altered. So by putting in this regularization term, it kind of hopefully makes the network safe against this kind of attack. So, and this is a big issue. A lot of people are sort of looking into this. You can imagine the applications of this in terms of biometrics. If they're trying to get rid of passports and just have people do a retinal scan or a thumbprint, or facial recognition. If you can get in and just slightly alter an image to fool a network, then it could have all sorts of security implications. Although, as I said, to do it in a really kind of spectacular way, you need to know the structure and the weights of the network. If someone's got a network that they're using and you actually don't know the weights, it's much harder to do this, but it's not impossible. Okay, so that's the contractive autoencoder. Now, again, the terminology, why is it called contractive? Well, I guess what it's saying is that these inputs lie on some sort of you can think of these inputs as occupying some sort of manifold in the input space, and this is saying that if the input, right, so this function f maps the images to the hidden units, and this is saying that if you make a small change in the input, you don't want to have a situation where a small change in the input creates a big change in the hidden units. You want it so that a small change. You want it so that a point that's slightly away from an input actually gets mapped. Ideally, if this input gets mapped to this hidden node, then something slightly away from that input should get mapped to the same point, or a close point. So that's why it's contractive, that this mapping is sort of not only the input, but a region around that input, a region of images around that input should all get kind of contractively mapped to the same point in hidden unit space. And finally, we have the related concept of the denoising autoencoder. So this is similar, but it doesn't rely on calculating those gradients. what we do is we simply say, okay, we've got a set of training images, but when we're training the network, instead of feeding in the actual image as a training item, we feed in a corrupted version of the image, right? So this is a bit like data augmentation, but the corrupted version is usually done by adding white noise to the image. So with the data augmentation, we shifted the image a little bit or changed the RGB colors. Here, what we're doing is actually adding white noise to the image. So the thing that I showed you with the panda, the thing in the middle was supposed to look a little bit like white noise, right? White noise is the thing when you've those old-fashioned TVs where you just had a static signal that was white noise. It's like a Gaussian, every pixel value is chosen from a little Gaussian distribution. So you corrupt the image by adding a bit of noise, but then you try to reconstruct not the noisy image, but the actual original image, right? So you attempt to train the network so that from the corrupted image, it actually reproduces the original image. So this has much the same effect as the contractive autoencoder, but is a bit simpler to implement in some ways. Okay, any questions about this? Okay, so let's expand a little bit more now on this issue I was talking about with the probability distribution in the latent variable Z. So we saw how the cost function at the output of a feed-forward neural network could be seen as defining a probability distribution over the outputs. So this is the same kind of terminology we saw with the reinforcement learning and so on. So we used theta to denote the weight values. And if I fix a particular set of thetas, then there's this probability distribution over the outputs that depends on theta, and then we were training in order to minimize the log of the, in order to maximize the log of the probability of the target values. So that we saw 3 different examples of this. So with the squared error, we assumed an underlying Gaussian distribution whose mean is the output of the network. So we went through this with the differentiating the Gaussian distribution to get this squared error. And the cross entropy assumes a Bernoulli distribution with probability equal to the output of the network. We went through this as well. So a Bernoulli distribution is just a fancy way of saying that you have a number between 0 and 1, and that directly tells you a probability. Normally we have the sigmoid. Normally we have a sigmoid activation there that forces the thing to be between 0 and 1. And then the other example we saw was the softmax. Now the softmax actually assumes a Boltzmann distribution. So if we did talk about the Boltzmann distribution in the last lecture, so this is just a fancy way of saying that the output, if a particular output is Zi, then the probability is proportional to e to the power of Zi, appropriately normalized. Okay, so when we think about this in relation to encoders and decoders, so for the autoencoder, if we choose a particular value z of the latent variables or the hidden variables, we can think of this as defining a probability distribution on the output x. So again, it's best if it's simplest if we think always in terms of images. So the latent variables are just the latent variables are not images. They're not spatial. They're just values that zi that vary and can be with a mean of 0 usually, but can be positive or negative. But then once you fix a certain value for these zi's, that gives you a probability distribution of the output x, which is an image. Okay? And sometimes there's also a conditional probability distribution. Sometimes when you put in an input image, it also defines a conditional probability over these latent variables z. And this, what we looked at last time with the restricted Boltzmann machine, fits into this terminology because both of these were Bernoulli distributions. So in terms of the Bernoulli distribution, the z's had to be either 0 or 1. So you feed in, what happened in that case was you feed in an x, you use these weights to calculate hidden values, but each hidden value is a number between 0 and 1, but then we use that as a probability to force, and we chose latent variables that actually were equal to 0 or 1 based on those probabilities. So if the sum of these weights was 0.4, then with probability 0.4, the thing would be equal to 1, and otherwise it would be equal to 0. Okay, so we saw this example before. Now we're going to kind of expand this to have a real kind of generative model. So this is what's happening here. Sorry, just to put this in context, this is it's basically what I was saying before, that when we train this, we then want to be able to choose a random z at the hidden layer to create an output. But what we're going to do is we're going to put in some extra we're going to put in some extra things that'll force the hidden unit variables to have a particular distribution. So everything we've seen so far, it has some effect on the hidden units, but doesn't really impose a particular distribution. But these variational autoencoders are actually going to do that. Okay, there we are. Okay, so as well as we're producing the training items, we also want to be able to use the decoder to generate new items which are similar in style to the training items. So if the training items are all images of bedrooms, we want to create images of bedrooms. If the training items are all images of people or faces, we would like the generated items to look like faces, and so on. So we would want to be able to choose latent variable z from a standard normal distribution, feed one of those values to the decoder, and we would then want it to produce an item x which is somehow similar to the training items. And so we're going to look at a couple of different ways to do that. So first we're going to look at variational autoencoders, and then in the second half we're going to look at these generative adversarial networks. Okay, so the variational autoencoder. Now, what happens with this variational autoencoder? We want to have this probability distribution, and usually we actually make it explicit. So we have a neural network that tells us a mean and a variance, not just the mean. Yeah, so the encoder produces a mean and a standard deviation. So the mean tells us, so if I put in a particular xi, there's this distribution. It's not just if I put in a particular image, it doesn't tell me just a particular value for the hidden variables, but it actually tells me a little bit about how much those values can vary, right? So the mean is I think of this as being a Gaussian distribution so this is the mean, so this is sort of the typical latent variables, and then the standard deviation tells me how much the latent variables can change in each hidden unit, but still being pretty much faithful to the original image. So you've got this mean and the standard deviation. Now, then what we do is we try to maximize this value here. So the first term says that, so the first term of this says that that if z is okay, so I put in a particular xi, and then I put in a particular image and I sample a hidden variable z, and then if I feed that that z into the decoder, what's the probability that it'll produce the input image? So this term here tells me the probability of reproducing the input image from that z. And then this term here is this KL divergence between the conditional probability here and a standard normal distribution. So this, I guess we maybe have to go back and look at the previous notes, but we talked about this KL divergence. This is a way of measuring the distance between two distributions, right? So on the one hand, we want to faithfully reproduce the input, but this term here is the one which forces the tries to force the hidden unit activations to match a standard normal distribution. This P of Z is a standard normal distribution. So how can we think about this? Well, so in effect, it's sort of stretching out. If you didn't have that second term, there would be a tendency for this distribution to collapse to a point. You know, it would just, the network would get very sort of fussy and say, okay, well, you've given me a particular input. I'm just going to map it to one particular hidden unit activation, and then I know that that activation is going to reproduce the input. But what this second term does is say, well, can't you stretch that distribution out a bit? I want you to stretch that distribution out and not only give me one point, but give me actually a set of points, and I want you to stretch it out as much as possible. So there's this kind of tension between these two terms. The second term is trying to stretch out the distribution to cover as much space as possible, but the first term is trying to make it so that all the points in that distribution will faithfully reproduce the input. So there's this tension between stretching out the distribution but having it such that it still reproduces the input. And so this, so if you look at this KL divergence, so on the one hand it stretches out, but it also tries to line it up so that the latent variables have a mean of 0 and don't just like wander off somewhere else. Yeah. Now, but interestingly, this is for every input, it's trying to stretch this distribution out to be the standard normal distribution. But what's going to happen in practice is that it'll stretch certain dimensions out more than others. Okay, I mean, I guess this is very waffly, but I hope that maybe this image here might make it a little bit more explicit what's actually going on. So this is a variational autoencoder that's been trained on this MNIST data set, and I'm not sure how many hidden nodes there are. I think there's maybe 3 or 4 hidden nodes, but they've done this principal component analysis to show only the 2 most important directions. And what you see here is, remember, it's unsupervised training. The digits, the same type of digit does tend to cluster into similar places. So you can see this group down here. So first of all, the whole thing does kind of represent something similar to a Gaussian distribution in 3 dimensions. You can see when we project it to 2 dimensions, it kind of looks like roughly like a circle. Not exactly, but roughly like a circle. And you can see that there's more, it's a bit hard to see, but the points are very dense in the middle and sort of sparse at the edge. So it's really like if there were 3 dimensions, it's actually kind of like a ball. That these things are actually more like a ball in 3 dimensions, but we've projected it so that we're only looking at 2 dimensions. And you see the digits that represent number 1 are these ones down here. The 0s are these ones here. The 6s are here. The 2s, the 3s, the 5s, the 9s, and the 7s. And so you get this kind of nice picture that the digits, even though it's unsupervised, the same digits do tend to agglomerate together, and related digits tend to be near each other. So 2 and 3, 8 is similar to 9 and also similar to 5. 5 is similar to 8 and 3. 3 is similar to 2, and you can sort of see how a 2 can smoothly morph into a 6 by this loop becoming a bit bigger and so on. And then there's this bit of a funny boundary here between 0 and 1. And naturally 1 can morph into 7 and so on. So this sort of thing kind of makes sense. But for every, just thinking about it in terms of this KL divergence, for every input you would have actually, so if I put in a particular input, it corresponds not only to a point here, but actually a little region here. And there's that second term is trying to stretch that region out to cover the entire. In each case, you're measuring the KL divergence between that distribution and the whole Gaussian distribution. So, but because of the tension that you also want to recreate the input, what happens in practice is that a certain type of digit stretches out to cover a certain region of this latent space. So the 1s occupy this region and the 7s occupy this region and so on, and together they're sort of largely separate, but between all of them, they cover this whole kind of distribution. And then once you have this, then if I pick any random point inside this ball, it'll create something that looks kind of like a digit. I hope that makes sense. Has anyone got any questions about this? Yeah?
Remember when we spoke about the KL divergence, it made a difference which distance?
Ah, yes, whether it was the forward or reverse.
What's it in this case?
Ah, good question. Let me think about this. It's trying to, okay, so it's the one that's, it gets penalized. Right, so the question was whether it was the forward or reverse KL divergence. So this distribution, it's a very good question. Let me put it this way. This distribution gets penalized for any part of this that it doesn't cover, right? So if we look at the KL divergence between, say, this and this is getting penalized for the fact that there's all of this that it doesn't include, basically. So it's trying to get the conditional distribution to stretch out and cover the entire thing. Yeah, so it's in that sense it's the forward KL divergence. So this is in contrast. Yeah, when we looked at deep reinforcement learning, if there were two strategies if there were two strategies in an Atari game which both achieved a high score, it was acceptable if you exclusively followed one strategy and never did the other one. Yeah, but here that's not the case. Here you are getting penalized for the fact that you're not covering the rest of that distribution. But it's this tension. Yeah, so there's this force trying to get you to cover the whole thing, but on the other hand, if you don't reproduce the input, you're getting penalized. So it's a trade-off between the two. But it does have the effect that between them, these things should cover everything because there's no advantage to leaving empty space kind of thing. Yep. Well, this is just the notation for the KL divergence. We put this double bar in here. It's called a divergence. Yeah, well, as we were discussing, it's not strictly speaking a distance because it's not symmetric. But we always write it with that double bar. It's just a notational thing. Yeah.
So if you measure the distance from P from the other one, you'd get a different value.
If you swap the two, it would be different. Yeah, that's right. Okay, we've only two or three more slides and then we'll take a little break. So this is an example of training on a variational autoencoder. So this is here we're using it as a generator. We train it and then we choose a random latent variable and see what image is produced. We do that 64 times. So in the beginning, it's after one epoch of, these are the original digits, these ones over here. After one epoch of training, it's producing things that are pretty fuzzy. They sort of vaguely look like digits, but they look pretty fuzzy. After 9 epochs of training, it's doing a pretty good job. It's producing things that do kind of look like digits. The only thing is that they're a little bit blurry, right? Now, if a digit is blurry, we don't really mind, but these variational autoencoders, when we start applying them to things other than digits, the blurriness kind of bothers us, and especially faces. You know, when we see these, I mean, this isn't bad. I mean, these things do kind of look like faces, but yeah, the blurriness we find off-putting, and so, but this was kind of the first serious attempt to generate, do a generative model of neural networks. So, what we're going to talk about after the break is generative adversarial networks, which do the same job as a variational encoder, but do it better. They produce kind of sharper, better-looking images, and you know, the basic GAN algorithm produces better images than a variational autoencoder, and there's all sorts of tricks that people use specifically for faces or in other situations that give even better results. So that's what we'll talk about after the break. Yeah. So we'll have a 10-minute break now. Good. Okay, so now we're going to talk about generative adversarial networks, but as always, I like to kind of look at the history of these things and the context of them. And really, this kind of fits into a general paradigm known as artist-critic coevolution. So we'll talk a little bit about that and different coevolutionary paradigms, and then we'll move on to the GANs. So what is artist-critic coevolution? Well, it's a system where you have an artist who's generating images, and then you have a set of real images, and you have an artist who's generating images, and then you have a critic, and the critic's job is to try to tell the difference between the real images and the ones that have been generated by the artist. Yeah, so you have this sort of system with two players, and the critic is rewarded for its ability to distinguish the real images from those generated by the artist. And the artist is rewarded for fooling the critic into thinking that the generated images are real. So this is a kind of slightly indirect method where it's not that the artist is trying to reproduce the real images. The artist is just trying to the fitness of the artist is filtered through the critic somehow. Now, this is a list of different ways this paradigm has manifested itself over the years. So in the early, and we'll talk a bit more detail about some of these things next week, just as a kind of extra topic. But in the early days, the human always played the role of the critic. So in the 1986, you had this, Richard Dawkins wrote this book called The Blind Watchmaker. This was back in the days when he was more interested in genetics rather than religion or anti-religion. And so he wrote this book called The Blind Watchmaker, and along with the book, they had this sort of system that was called biomorphs. And the graphics were very hokey. This is 1986, but the way it worked was that 15 images would be randomly generated using these kind of Lindenmayer systems, and then a human user would select one or more images that they liked, and then those images would go through a breeding process, and it would try to create new images that were similar to those images but not quite the same, and then you'd repeat the cycle. So you'd get 15 more images and you'd click, and then you'd keep going like this. And remember, this is like the hokey graphics of 1986, but if you have some imagination, you could perhaps create, after several generations of this process, you could create images that maybe look like a man in a hat or a Spitfire or a spider or a lamp. You know, you need a bit of imagination, but these things are quite sort of cute. Now, you fast forward to 1991, and Carl Sims kind of re-implemented this in a bit using slightly more sophisticated computation. Now, I won't go into all the details of this, but he used something called a genetic program to generate the image. And in this case, the genetic program acts as a function. It's given an X and Y value, and it tells you a red, green, and blue intensities for that X and Y value. So if you feed in all the X and Y values for all the pixels in a frame, you can get an image, and he has certain mutation and crossover operators and whatever, and anyway, it's the same paradigm. 15 images appear on the screen, and the human picks, and after a while this is one of the images that emerged from his system. And then if we go forward even more to 2011, we have the pick breeder system, which again works on the same principles, but it's instead of just the artist is actually this thing called a compositional pattern producing network, a CPPN, and eventually there's this website pickbreeder.org that you can go to and play with this, and eventually you can actually get some pretty nice looking images like this, that look like an apple or the earth or Jupiter or the face of a pig or a candle. This is very, very nice, but it's very cool, but it does require a fair bit of human effort. It may require 100 or 150 generations to produce an image of this quality. So you're sitting there and clicking, and it can become quite laborious. And so it's natural to ask, well, can the human be replaced by an automated critic? And now, as I said, next week I'll look at some other frameworks where this has been done, including some very recent work I've been doing with computer-generated art. But for today, I just want to focus mainly on GANs. But I'll just make the point that depending on what kind of artist you have, you get different styles of picture. So this is the biomorphs. This is generated similarly to the Carl Sims 1991 things. This is a pick breeder. This is some work using a cellular automaton to generate images, and these are some images from my own work where you're using like a drawing program which specifies a pen color and thickness and gives instructions about where to put the pen down and up and so on. And these are using a function to tell you the red, green, and blue values at a certain X and Y value, but with a particular kind of genetic program. And this here is an image from a generative adversarial network, and among all of these, the generative adversarial networks definitely produce the most realistic looking images. Okay, so what's going on here? Now the artist, with the GANs, we normally talk about a generator and a discriminator rather than an artist and a critic. And what happens with the GANs is both the generator and the discriminator are neural networks, deep convolutional neural networks. And so the generator, we use theta to represent the parameters or the weights in the generator network, and we use psi to represent the weights in the discriminator network. And so the generator maps. So again, we try to follow. By the way, this is one of the interesting things. This shows you how quickly this field is moving. Is that this topic of generative adversarial networks is hardly covered at all in the textbook, despite the fact that the main author of the textbook, Goodfellow, is like a world-leading expert in generative adversarial networks. So the reason it's hardly mentioned is because when the textbook was written in 2014 or 15, this hardly existed. So that shows you it's just how modern this is. Okay, but I've tried to use standard terminology and terminology that's consistent with other things in the textbook. So we use Z to represent the latent variables. So the generator is actually playing the role that was previously played by the top half of the variational autoencoder. So it's trying to map these latent variables to an image, x, and it has parameters theta. And we don't explicitly, so with the variational autoencoders, we explicitly had a mean and a standard deviation. With this, we don't have explicitly a mean and a standard deviation. So I think that's the reason that this is sometimes called an implicit model, whereas the variational autoencoder is called an explicit model. I find it a bit confusing, this implicit and explicit, but I think that's what's intended here. So the generator, you generate a random variable z from a Gaussian distribution. So if z has 100, if there's 100 components to z, every component is randomly selected from a Gaussian distribution with mean 0 and variance 1, and you feed that into this generator network, and an image pops out the other end. Right? Now, the discriminator network takes an image and it maps it to a number, because remember, so this is kind of like a classification task, but there's only two classes, right? Because there's only two classes, we really only need one output. Sometimes we may have two outputs, but we only need one. And so the discriminator produces a number between 0 and 1, and that indicates its estimate of the probability of the image being real. So usually, it kind of varies, sometimes different papers, but usually a number close to 1 means that it thinks the image is real, and a value close to 0 means it thinks the image is fake. And so it's kind of like a two-player zero-sum game, right? The discriminator is trying to assign values close to 1 for the real images and values close to 0 for the images coming from the generator. And the generator is trying to generate images which the discriminator will assign a value close to 1. And so, remember the discriminator parameters are psi and the generator parameters are theta. So the discriminator is trying to maximize this expression, and the generator is trying to minimize it. So what is this expression? Well, when you choose an when you choose an image from the actual set of images, the discriminator wants the log of its output to be high, right? So the log, again, the number is between 0 and 1, so the log of 1 is 0, and the log of a number less than 1 is a negative number, which diverges to negative infinity as the number goes to 0, but it diverges quite slowly. So if this number here is always negative, but if the discriminator is assigning values close to 1 for these real images, then this number will be as large as it can be, right? It's a negative number, but it'll be close to 0, right? Which is what you want. Now, what about this? Well, so so that's if an image is chosen. So you alternate between feeding it real images and feeding it images generated by the generator. So if it's a generated image, you randomly choose Z, you feed that Z into the generator and an image comes out, and then you feed that image into the discriminator. But in this case, you want the log of 1 minus that to be large. The discriminator wants the log of 1 minus that to be large, right? So it's trying to produce a value close to 0 for those images. Yep. Now, so the discriminator is trying to maximize this. Now the generator is trying to minimize it, but remember the discriminator doesn't have any effect. The discriminator can't do the generator can't do anything about this. It's not involved in that part, but it's trying to generate images for which the discriminator will assign a value close to 1, which will therefore make this value small, right? Okay, any questions about this? Yeah. Yeah?
Are they both trained at the same time? You train the generator?
They're both trained at the same time. I'll get to the details of the training in a minute, but they're both trained at the same time. Yeah, you don't train the generator first and then well, actually, it's a good question. Since you asked, let me talk about this. So if you were to, I'll show you some examples of this next week, but if you like, let's say, well, there's been some examples where you take ImageNet. Like ImageNet is a pre-trained network that you can feed in an image and it'll try to tell you what category that image is, right? So you could use ImageNet as your discriminator and then feed in, and then try to train a generator network that will fool ImageNet. And it actually, what happens is it will produce, in that case, it can produce images that will fool the network, but it can produce an image that the network is convinced is a tiger, but actually to us it doesn't look anything like a tiger. It might look like just some black and yellow stripes. Actually, sorry, since you asked, we have a bit of time, let me just show you some of these images. So this is, I'm not sure, I think a CPPN was used to generate these images rather than a convolutional network, but it illustrates the point. This is work out of Jeff Clune's lab. These are images which ImageNet, these are generated images which ImageNet assigns a particular category with very high confidence, but to us they just look like weird stuff, right? So it's absolutely, ImageNet is convinced that this is a comic book and that's a stethoscope and that's a, well, actually, that's not too bad. That does look a bit like a strawberry. But the real point is that because in this case the discriminator is pre-trained and then fixed, it kind of gives the generator an unfair advantage, right? So this is a lot of the importance with the artist-critic coevolution, and the fact that the discriminator and generator are trained simultaneously takes away that advantage, because once the generator starts to fool the discriminator then has an opportunity to adjust itself. Yeah. So what you ask is actually a very good question. Yeah. Okay, so there's one slight change to this that's usually used with GANs. So this is the expression that I had on the previous slide. So I said that the generator would try to minimize this part here, but in a way there's something, this formula kind of puts in a way too much emphasis on images that are correctly classified. it's better to do gradient descent using this instead of that. So what's going on here? Well, this is this heavily penalizes. This puts more emphasis on images that are wrongly classified. So if the generator, sorry, if we go back to the original, this log of 1 minus d is, well, the place where it's going to put the place where it's going to give the heaviest penalty is where you're calculating a log of something close to 0. So that log of that thing is going to be close to 0 when d of g is close to 1, which means that that it is successfully fooling the critic, whereas here log of this is this thing is going to be close to 0 in situations where the generator is failing to deceive the discriminator, right? So this thing here actually gives much better results. It puts the emphasis on the images where the generator is failing and really tries to lift them up rather than emphasizing the ones where it's already doing well and trying to make it do a bit better. Yeah. So this is what's usually happened. This is the way GANs are usually trained, but the discriminator is normally trained using this original function. Yeah. So it's actually, so when you swap it around like this, it's not quite a zero-sum game, but it's because the generator and discriminator are putting emphasis on different things. But anyway, but this tends to give somewhat better results. Okay, so the details. So one network aims to produce so the generator aims to produce the full range of images X with different values for the latent variables. Now, one interesting thing about this, the differentials are back propagated through the discriminator and into the generator. I don't know. Wasn't quite sure what order to present these things, but maybe we'll look at this pseudocode first and then look at the architecture. So this is the way the training is usually done. At each epoch, you sample a mini batch of latent samples, Z1 up to Zm, and you also sample a mini match of real images, X1 up to Xm, and then the discriminator is trained on this by gradient descent on its parameters to maximize this. So you're balancing an equal number. I mean, all these things are interrelated, but if you think back to the Word2 Vec model, how we had a positive, we had negative sampling. Here we try in each batch we try to balance the number of positive and negative examples. If we have M real images and M generated images, and then for the generator, we sample M latent variables. We use them as a generator, and then we feed them to the discriminator. So I guess you were the one who asked whether they're being trained at the same time. They're both being trained in the same epoch, but within the epoch, I guess it is kind of separated into two. One where the generator is trained and one where the discriminator is trained. So in this top part, only the discriminator is trained and not the generator. In the bottom part, only the generator is trained and not the discriminator. This is the way it's usually done. So we And normally these samples are different from, I think that these samples are normally different from those samples. We actually train on a completely new set of samples, and we don't train on if we were to train the discriminator here, then the thing would become unbalanced. We'd have 2 M negatives and only M positives. Yeah, so this gives slightly better results than if we use the same samples and train both at once. I'm not sure why. It's just one of those things, you know. But the important point is that okay, so let me talk about the architecture. So the discriminator, you can imagine the discriminator is very, very similar to ImageNet or LeNet, those convolutional networks that we already talked about. The only difference is instead of having 10 outputs for 10 different digits, we only have 1 output, right? So that part of the story you know. Now what about the generator? Well, the generator is a kind of a convolutional neural network in reverse. Sometimes it's referred to as a deconvolutional network. So if it was, so the discriminator, you start with convolutional layers that get smaller and smaller, and then you have fully connected layers. So the generator, you start with fully connected layers, and then you move to convolutional layers. So it's like the inverse of a convolutional layer. But when we train, the important thing is this is the generator, and then you stick the discriminator on the end of it. And when we train the generator, we backpropagate the differentials from the discriminator into the generator. So there's a discriminator on the other side of this. Because it's generated, it's always trained to whatever the output is of the discriminator, you backpropagate through the discriminator, you get certain differentials at the image, and then you continue to backpropagate those differentials into the generator. So you're actually backpropagating from one network into the other. So even if we're not so when we do this part here, we are actually, we're not updating the weights for the discriminator, but we are calculating the differentials for the discriminator so that we can train the generator. That makes sense. Okay, so okay, now these are just some details. Again, this has been sort of worked out from trial and error, what works best. Normally, they normalize the images to be between -1 and 1. For some reason, this gets better results. So black is -1 and white is +1 rather than 0 and 1. Now, as I mentioned, we don't have pooling layers because it's too hard to reverse pooling. So instead, what we have is, for the discriminator, we have strided convolutions, which we previously talked about. And for the generator, we have the reverse process, which is called fractional strided convolutions. We tend to use batch norm in both the generator and discriminator. So we talked about the vanishing and exploding gradients. So batch norm is a way of dealing with that. For deeper architectures, we tend not to have fully connected layers at all in the network. It's just completely convolutional. At the output layer of the generator, we tend to have tan H because it has to produce something between 0 and 1. It has to be an actual image. At all the other layers, they use ReLU, and for the discriminator, they use leaky ReLU. So again, these are just things that they tried various options, and this turned out to be the best. Now, these are Okay, so let's look at some results. So these are, I kept talking about bedrooms, so this is a classical paper from 2016 which generates bedrooms. There's been a lot of improvements since then. Now these look pretty impressive, these images, at least compared to what had been done before. If you look very closely, you might see some anomalies in this image, in these images. So this bed is a bit of a funny shape. It's not really quite shaped like a bed. Here, you've got perhaps maybe Siamese beds that are joined together somehow. So yeah, if you kind of look really closely, you can see things that don't quite look natural, but there's been a lot of effort to kind of get rid of those anomalies. This is, and now we talked, when we looked at the linguistic stuff, we looked at king plus woman minus man equals queen, or this sort of thing. You can do the same thing with images. You can take a smiling woman minus a neutral woman plus a neutral man and hopefully get a smiling man. Looks a bit demonic, but not too bad. It's a bit easier to add sunglasses. So you can take a man with glasses, subtract a man without glasses, and add a woman with glasses, and you get a woman with, add a woman without glasses and you get a woman with glasses. I'm not sure, if you try to do the process in reverse, it might look a bit more strange. You know, somehow it's easy to cover up the eyes rather than include them, but these results are pretty good. Now, okay, some issues with GANs though. It's a bit tricky to train a GAN. You have to kind of adjust the variables very carefully. Because it's a coevolution, GANs can sometimes oscillate or get stuck in a mediocre stable state. So we'll talk in a bit more detail, more generally about this next week. But in the case of GANs, there are two ways in which if it goes wrong, there are two ways in which it often goes wrong. So one is that the GAN may train for a long, so one's called oscillation, where the GAN kind of trains for a long time and it does generate a variety of images but somehow fails to improve. So the nature of the images kind of oscillates or switches around. So for a while it may generate images of a particular, it may prefer for a while generating images of a particular type, and then it may switch and start generating more images of another type, and then it may later go back to the first type, but the quality may be not any better than what it made before. So it may sort of switch around but not show real improvement. The other problem is called mode collapse. So this is where the generator produces only a small subset of the desired range of images or converges to a single image with minor variation. So this is if you look carefully at this objective function, the generator is only required to, so if we go back, you know, the generator is rewarded for its ability to produce images that fool the discriminator, but it's possible that the generator might only produce some very small, I don't know, like let's say the generator is supposed to produce, you know, maybe the reference images contain, I don't know if this is a good example, but faces, you know, the reference images might contain men and women, black people, Asian people, and so on, but the generator may only produce images of white men, for example, but they may be very convincing enough to fool the discriminator. From what I've written here, there's nothing to prevent that from happening. The only thing to prevent it is if the generator does concentrate only on that subset of images, then maybe the discriminator will become better at knocking those out, and that might cause the generator to then explore something else, but that's a very indirect effect. That might not happen. So these in practice, these are quite big problems for GANs, is this oscillation and mode collapse. Okay. Now, there are methods for avoiding the mode collapse. We won't be going into these in detail, but I just mentioned them. You can have a look for yourself. So conditioning, augmentation, mini-batch features. This is like fitness sharing, where you try to reward the generator for the variety of images, and there's also something called unrolled GAN. So there are, I guess, really, I just want to say these are serious issues, but there are ways people have been looking at to try to deal with them. And there's been so much work on GANs. Someone referred to this as the GAN zoo because there was like A GANs and B GANs and N GANs and whatever. There were so many different types of GANs, and this is just a non-exhaustive list of them. Yeah, so you can see what a big area this is. Okay, so let me just, two things. I just want to look at some images and videos of maybe some of the latest work, but I just come back to this. So one of the reasons that GANs, why is it that GANs do a better job than, say, variational autoencoders? Well, one of the reasons is this. So let's think about this for a minute. So what this is saying is that this provides potentially a mechanism for the generator to fool the discriminator, right? Maybe the generator figures out if I adjust the image in a certain way, the generator will be fooled into thinking it's a real image, right? But when it does that, then the discriminator has an opportunity to correct it. You know, at first the discriminator will be fooled, but then remember the discriminator is being trained then to reject the image that the generator generated. So there's this kind of adversarial, that's why it's adversarial training, that the generator finds a way to exploit the discriminator, but then the discriminator kind of patches up that loophole or closes off that means of exploitation, and then the generator has to look for something more sophisticated to try to fool the next discriminator. Okay. Now, I wanted to show you, there's just been a lot of talk about this recently. So people have been using, just a few examples here that I've sort of randomly found. This is a sort of adaptation where you start with a line drawing and try to produce a face that matches that line drawing. These ones are pretty good. Those ones look a bit strange. There are GANs there are particular tricks that people use for faces, and I believe all of these images here are synthetically generated celebrities. And that one looks a bit like Taylor Swift, doesn't it? But it's not. It's fake Taylor Swift. This is so much better than what we saw with those variational autoencoders. Yeah, so even, no one's job is safe from automation. Even Hollywood superstars might be replaced by computers in the not too distant future. There's also this method of super resolution. Sometimes the output of a GAN initially looks like this, but can have a process that sort of refines it to this. Okay, so I wanted to, but the more interesting thing people have been looking. Oh, okay. Let's have a look at a couple of these. This is turning a horse into a zebra. So this is examples of other things you can do with GANs. So you've got an image of a horse, and you can turn it into. You can see that it stripes. Yeah, it stripes the. Let's try to catch that. You can see that it's putting stripes on the pole. So it's not perfect, but it's pretty reasonable. Now, but the more interesting thing is you can take a celebrity and try to make a fake image of that celebrity. So they think this was some footage that was created of Barack Obama. Sorry, we can't. Let me see if I can get the audio here. We might not be able to hear the audio, but I'll see if I can get it a different way. I'll just do it like this because it wouldn't work for some reason that way.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet. It's a time when we need to rely on trusted news sources. It may sound basic, but how we move forward in the age of information is going to be the difference between whether we survive or whether we become some kind of fucked up dystopia. Thank you. And stay woke, bitches.
I apologize for the.
Which our enemies can make it look like.
I apologize for the bad language. Obviously, this isn't simply GAN. I mean, this isn't just GANs. They have extra. They have all sorts of other sort of facial frames and stuff like this. It's it's a whole lot of techniques all brought together, but you can see what's possible with this. And again, I like to give the historical context of this. The first time I couldn't find the video of this, but something similar to this, but quite a lot more primitive, was actually presented in 1994 at SIGGRAPH, and there was a video made of John F. Kennedy saying quite strange things and singing nursery rhymes. And it was done without neural networks. It was done with like old-fashioned image processing features and things like this and voxels. But for the time, it created a lot of discussion even back then. Like people saw the implications of this and had a big discussion about it even back in those days. But of course, you would have to recreate the person's voice, and this is so those Hollywood. One of the reasons those Hollywood actors aren't out of a job yet is because it's we can't yet reproduce the voice as good as actual human actors, but the day is probably coming when that can be done. And so this is other techniques that have been used to try to this is recreating John F. Kennedy's voice.
In a world full of frustrations and irritation.
I think this is when he was assassinated. He was on his way to deliver a speech, and this is actually the text of the speech that he was going to deliver.
America's leadership must be guided by the lights of learning and reason, or else those who confuse rhetoric with reality and the plausible with the possible will gain the popular ascendance with their seemingly swift and simple solutions to every world problem. There will always be dissident voices heard in the land expressing opposition without alternatives.
I love the way it seems like they've added a bit of static to make it sound vintage as well. But you can see the potential of this, right? If you synthesize the voice and then synthesize the video to go with it, you could really create videos that are very difficult to distinguish from reality.
How far is it possible to recognize the real and this synthetic? Because it's going to be very dangerous for fake news, this sort of stuff.
It's a good question. I mean, I think it's it's getting harder and harder to tell what's real and what's fake, probably. Don't trust anything. And of course, with Trump, when Trump says things, they're so crazy anyway, it's really hard to tell whether it's fake or not. Okay, I think that's probably enough for today. But I'll just might take a few minutes just to go. I think there might have been one set of exercises we hadn't gone over yet. So maybe I'll just have a quick look at those, and then we'll wind it up. Let's see. I think we went through everything but not these Hopfield networks. Let me see if I can get this. We had trouble with this document camera before. Let me see if we can get it up this time. One out of two. Oh, yes. Okay, so let's let me just try to find these exercises. Oh, yeah, so this was about Hopfield networks and Boltzmann machines. So the first question was a bit, I think I copied this from a colleague who used to teach this course. It's a bit of a trick question. Can the vector 0, 1, 0, minus 1, 0, 1 be stored in a 5-neuron discrete Hopfield network? If so, what would be the weight matrix for a Hopfield network with just that vector stored in it? If not, why not? Well, actually, this can't be the weights of a Hopfield network. Does anyone know why? Yeah, it's actually a Hopfield network is actually minus 1 and 1. So it's not allowed to have the zeros. Okay, so let's look at this. Compute the weight matrix for a Hopfield network with 2 memory vectors stored in it, and confirm that both these vectors are stable states for the network. So these answers are already posted, I think. So all right, well, what does this actually, what are these vectors? So you've got 6 nodes in this Hopfield network. So one state that's stored is 1 minus 1, 1 minus 1, 1, 1, and the other state is 1, 1, 1, minus 1, minus 1, minus 1. And so you compute the outer product of each of these weights. So we look at which weights. So this outer product means which pairs of nodes have the same weight versus a different weight. So that minus 1 means that these two nodes have opposite weights. But this plus 1 means these two nodes have the same weight. And like if you, with a Hopfield, when we train a Hopfield network, we put zeros on the diagonal, but every weight here represents a connection between two nodes. So if you look at this node 2 and node 4, there's a plus 1 here because these two are the same. For that, these two have the same value. So these weights to show for that particular thing whether they have the same value or a different value. And this is the same for here. You can see this regular pattern. These 3 nodes all have the same value. These have the same value, but whenever you take one of these and one of these, they've got opposite values. Right? So when we want to store those vectors in the Hopfield network, we add these two matrices up and multiply by some normalizing constant. So we divide by the number of weights. We divide by the number of nodes, but add these things up. And so what we get is 1/3. Whenever we add plus or minus 1, we either get 0, plus 2, or minus 2, and then we're dividing the thing by 6. So I've just written it as 1/3 times this matrix here. So you can see what this matrix represents here. So this entry here is saying that if you look at the first and the second node, sometimes they're the same and sometimes they're different. So that's why it's a 0. But if you look at the first and the third node, they're always the same, or they're the same in both of these cases. And the first and the fourth node is different in both cases. Yeah, so this matrix represents, it encodes the information about whether certain pairs of nodes are likely to be the same or different. Now, confirm that both these vectors are stable. So if, let's say we have this matrix here, so let's say the network starts in this state. At a certain time, the network has this state, then what's going to be the network at the next state? Well, effectively what we're doing is multiplying this matrix by that vector. So this is 1 minus 1, 1 minus 1, 1, 1, and a third out here. So okay, what is this? Well, 1 times 1 and minus 1 times minus 1, so that's 2. Minus 1 minus 1, so that's minus 2. And we sort of, what is this? 1 plus 1 is 2. Minus 1 is minus 2. 1 plus 1 is 2, and 1 plus 1 is 2. So whenever this number is positive, the next state will be 1, and whenever this is negative, the next state will be minus 1, and so you can see that it's actually preserved. The next state will be 1 minus 1, 1 minus 1, 1, 1, which is exactly what it was before. So that's a stable state of the network, and you can do the same for the other. If you feed this one in, it's also stable. Okay, any questions about this? Yeah? Ah, the 1/3. Well, okay, yeah, sorry. The 1/3 should be here. But actually, it's only the sign. When we decide the next state of the network has to be +1 or -1. So if it's positive, we make the thing +1, and if it's negative, we make it -1. Yeah. The 2 doesn't matter for this purpose. That's right. Yeah. Okay. Now the next question. So let's just go back to the question. So consider the following weight matrix W. So if you start with 1, 1, 1, 1, minus 1, what will be the future states? And you're asked to do it using both synchronous and asynchronous updates. All right, so that's the weight matrix. And then the current state of this network is 1, 1, 1, 1, minus 1. So if we want to compute the next state, we again do this matrix multiplication, and if you go through this, it turns out to be 0, minus 0.4, 0, minus 0.4, and 0. Right, now this is where the weight updates can be either synchronous or asynchronous. So if it's synchronous, that means that all the weights update at once, which means the next state, yeah, I don't know why I did it in this order, but let's take it in the other order. Let's say that we're doing it with synchronous updates. So the nodes, if this is -1, if this is negative, then that node will switch to -1. But the rule is that if this calculates to 0, then the thing stays in whatever state it was in before. So the thing that was 1 will stay as 1, and the thing that was -1 will stay as -1. So if we do synchronous update, the next state will be this. So we started with 1, 1, 1, 1, -1, and we switched to 1, -1, 1, -1, -1. And then you can check that this is actually a stable state. If we multiply that matrix by this, it recreates the same vector. Now what happens if the update is asynchronous? Well, that asynchronous means that you're just changing the neuron. You're not changing everything all at once. You're changing them in a random order. You pick a random node and update it, and then you pick another node and update it. And so what happens here? Well, if the ones that are a 0, if neuron 1, 3, or 5 updates, then because of the 0, it just stays where it is. So whichever of these two updates first will switch to -1. So if neuron 2 updates first, it'll change to -1. And then in that case, you would get this vector here, 1, -1, 1, 1, -1. If neuron 4 updates first, then you'll get 1, 1, 1, minus 1, minus 1. So whichever of these two updates first is going to switch to minus 1, but the other one at first will stay as plus 1. But then when it's time for the other one to flip, it'll go to minus 1. So in both cases, you're going to eventually end up with this state which is stable. Okay, any questions about that? Yeah.
Is the method update in any order?
Yeah, so asynchronous means it can update in any order. So basically what will happen is whichever of these two nodes updates first will change to minus 1, and then when the other one updates, it'll also change to minus 1. So in this case, it doesn't really... So in this particular case, no matter what order, you end up in the same... no matter what order they update, you end up in the same stable state. But it could happen, for some other examples, it could happen that depending on what order you update them, you may go into two different stable states. Yeah. Any other questions? Good, okay. I think we'll have a half-hour early mark today. And then next week I'll talk a little bit more about this adversarial artist-critic coevolution and some other issues.